if you're all set, then it's my pleasure to kind of hand over in a minute to Carmela Troncoso, who's our final speaker, and whose work has been extremely influential within the last year for sure, but obviously also before. She's got quite a distinguished career, coming especially originally from Spain. She went through the COSIC group to get her PhD. She also did a postdoc there. She worked in industry. She went back to academia, and she has been with EPFL now for a while, where she heads the so-called Spring Lab, which is all about privacy and making this work in practice as far as I can tell. She's done a wide range, in fact, of scientific works, and she publishes quite widely across not just the sort of core ISCR range of conferences, but also at ACM, CCS, USNIX, and the like. Some of her current research interests, as far as I can tell, range quite a bit beyond what is sort of the traditional cryptographer's point of view. There's some interest in machine learning and how it will impact on us when it's also in the intersection with cybersecurity. And there's, I think, quite what I like, a really good focus on trying to get something that actually works, not just in theory, but in practice. So the whole aspect of engineering for privacy is something that I find very appealing. And I'm looking forward to hearing more about it from her over the next 40, 50 minutes. And with that, I'd just like to hand over to Carmela.
Thank you very much, Elizabeth. Thank you very much for the invitation. It's a pleasure to be here. Let me try to share my screen. So before I start, let me shamelessly announce that I have a postdoctoral position. Indeed, as Elizabeth says, we work on privacy engineering. We really like to deploy things. We try to get everything we do to actually something that is a product. We work a lot with NGOs because they really care about developing responsible technologies that don't damage their beneficiaries. And today I'll talk about our work on the contact tracing apps. If you like to talk, then please drop me an email and we can talk about it. So what I'm going to talk today is about how to engineer privacy. As Elizabeth says, I'm not a cryptographer. I was very scared when I received this invitation. It's like, what I'm going to tell these people. So what I want to talk about is a bit about the constraints that we have when we take that crypto and we want to put it into something that has to be deployed, and how not only the core crypto is important for the privacy of the system, but how the rest of the components and how they kind of build a puzzle. We also need, every time we put a new puzzle in, a new piece in the puzzle, also take care about the privacy that it brings, the problem that it has, and how we had to go, in the case of the contact tracing apps, from a very small and very simple protocol to full set and range of privacy technologies that we had to develop on the fly at a speed that I never imagined. So the work that I'm going to present here is not only mine. There is a huge amount of people that were with me in this. Well, in the beginning, it was a sprint. Not really, it was a marathon, and by now is this Ironman, in which we're still here because we're still doing work for trying to ensure that the technologies that are used in order to help with pandemic mitigations do not become a new problem, right? Technology is great, technology can help, but it has two sides, the good and the bad, and we try to make sure that only the good is there at the end of the day. And when I got to this project, it's not that I was particularly interested in building apps. I knew nothing about epidemiology, but our epidemiologist at EPFL called on us to help building this system, where the idea is that a main tool that epidemiologists and the health system in general has to contain pandemics and epidemics from spreading is what is called contact tracing, which by now, if someone has never heard about it, it is about the idea that so diseases transmit while there is a period in which you don't have symptoms, but you're still transmitting the disease. So in order to cut down how many people are infected, it is important that if you are suspected of actually being in that transmission period, and how you get to be a suspect is by being in contact with someone that actually has been diagnosed positive, then we should contact you and ask you to please take a test or take measures, quarantine, something, so that we can stop this, in particular for COVID, this exponential growth of cases. And the problem with COVID is this exponential thing, which means that the number of cases is so large that the manual tracing, this process that traditionally they would do through interviews and calling people, was overwhelmed, right? Not only that, but also the fact that COVID transmits very much on the air, and many times the people that we infect, we don't know them. So even if you go through an interview, you may not know actually who are those people, because how do you know the name or the phone of the person that goes with you on the metro, even though you may have spent with them half an hour going to work, right? So there was a need, and there was a question, can we have technology to complement this system? And one thing that we realized very fast is that even though the contact tracing system is based on identify and then call people, actually the goal is to notify. And this is kind of the first step of privacy engineering, and something that we do a lot now. You saw before that we work with different partners, and we work with them is to try to understand what's the goal that they want to achieve. We're not really interested in what are the solutions they have nowadays, because it turns out that technology has many more possibilities many times than the physical world. And we want to know what's the goal, to see if we can get to that goal maybe in a different way. In the case of contact tracing, the goal is to notify people, not really to identify them. Identify them is then just the means to get their phone numbers or their addresses to be able to notify them. But it is not something that is needed in order to actually get the service. So we wanted to have something that allows to notify users, and this needs to be timely. This is extremely important in the case of COVID, because the disease spreads so fast that we need to be as fast as possible in telling these people. It's to be efficient. If we need as many people as the manual tracing, then we're not helping them, because we don't have more people. We're trying to introduce technology because manually this cannot be held anymore, and scalable, because the number of cases of COVID, both locally and globally, are growing at a way that we cannot, like, if this thing only scales for 1,000 of people, then we haven't gained anything. And the main constraints in the beginning kind of were these things: security and privacy. We're going to put an app, it's going to be horrible, surveillance, yeah, all of these kind of things that we have. And indeed, this is very important, right? Because we're now going to ask people, when I came to this thing, we're going to ask not only of the people of Switzerland. We were talking at that point about a pan-European contact tracing digital system. So 500 million people in Europe, that they would expand to all of the millions of the people in the world. So it was very important for my team to make sure that this technology that we were going to put out there, as I said before, didn't become another problem. So we needed to protect this technology from misuse. And notice that I'm going beyond privacy. Privacy is not the goal. Privacy is the means that we have to actually protect ourselves from things that we don't like surveillance, like manipulation, the kind of things that then the fact that losing our privacy can have back on us. And for this, we needed something that could be only used for this particular purpose, that is to notify. So we wanted to build something that has purpose limitation by default. If we go back to the data protection regulation, purpose limitation means that the technology can only be used for its purpose. Typically, that is achieved legally, because you have a contract and you say, well, I'm going to collect all your data, but I'm not going to use it for anything else. But we wanted to ensure that this was done from a technological perspective, so that there is no temptation, because we have history telling us that once data is there, data will be used. And inside this pandemic, we already have like a bunch of examples, like phones collected by bars being used by bartenders to call this pretty girl that's having a wine today. We have the police asking for some records of contact tracing. We have a lot of these things, and we wanted to avoid this. And to avoid things from misuse, there are three things that we know have been misused many times in the past. One is the identity of the users. The other one is their location, where have they been? And this not only has a lot of rich information in terms of identity. We know that if you have fine-grained location traces, it's very easy to recover who are the people in these traces, especially because they live in their homes and they work where they work. And it turns out that the temple address of where you live and workplace is almost unique. And now we start to think about people you know or yourself, and how many people you know, except for academic couples. I know we're a lot of those, but except for those, how many live on the same house and work at the same place? Probably not so many. And also they encode a lot of information about our likes, what we like, what our costumes, what kind of things that we like to do, how often do we do it. And then there is this kind of social behavior. Who do you talk with? Who do you see? How often do you see them? How long do you speak with them? Would you see them? And it can also be very much indicating if you also know where you sit. And of course, we have that privacy is not the only thing. We need a system that is actually secure, in the sense that false alarms are very hard to trigger. We want that if a notification arrives, people really believe and can believe that this notification is for sure, and they need to take it seriously. And that is robust against denial of service, because if we put the technology on the pocket of 500 million people, but then it's easy to take it down, then we just have introduced a risk for nothing. And that's how we started, and that's how also I start my papers, right? Like this thing. But then there was a hidden constraint that I didn't know about when I came into this game, and this hidden constraint for the academia, right? We never tried to see it, but it's called reality. And reality was there. And the first kind of reality thing, I said it before, is that this thing had to be highly scalable. Normally, when we talk about scalable, we think scalable, we think even like in papers, like 1 million users. I'm not talking about a million. I'm talking about 1 billion users in the world. And then reliable. We're going to rely on this to help us go out of the pandemic. It cannot be that we put it out there and then the next day it just falls down, or it is not very good, it is complicated, people cannot know. This has to be very reliable. But kind of the one that was really, really a hit for me was the time pressure. In the first meeting, I was with this big consortium when it all started. The people that were saying, okay, we're going to build this thing, they said, we're going to have an app on the market, on the phone market for people to download in 3 weeks. 3, right? This is not agile. This is beyond agile. Like in 3 weeks, and then a normal company, you don't even have an idea. In 3 weeks, like you got to talk to your student about a notion of a problem that you may want to talk with. Here we had this thing. In the end, it didn't happen in 3 weeks, but it did actually from the inception of the problem till the first prototype, it was like a month and a half. Like no product has gone from inception to deployment in such a short time, as far as I'm concerned. But this time pressure, and it meant that we needed something that we could design very fast, but also was very robust and was easy to verify. Yeah, like following this KISS principle, keep it simple, stupid. This is one of my first slides in my computer security course, and I never knew that I was going to feel it so kind of close to me, right? But we needed something that we could put out there, and we could check and be very, very sure that the protocol, I mean, it may have, it may not be perfect, of course, because there is nothing that is 100% secure, but we need to be able to say that the properties we promise are the properties that are given. And that meant that we could not use non-kind of mainstream type of crypto. Like I have papers with very cool commitment schemes and new private set intersections that are very fast and very cool zero knowledge proofs. But none of these was really kind of at grasp, because we could not produce one of these and make sure that our protocol, as well as the implementation, were secure in the amount of time that we had. That also meant that we could not go for other type of fancy kind of technologies that I also use on my papers, like using anonymous communications. Like even Tor, which is kind of actually pretty robust, is still on the 2 million users. We don't know what happens if now we hit Tor with every day, like 50 million users in Europe having these apps now going for it. And 50 million is not what we're going for, right? We're going for everyone. Again, we want 500 million Europeans hitting this type of network. So we could not really rely on all of those things. And that also meant that we needed to use existing infrastructure, or if we were going to set up a server or something, it had to be very, very, very simple. And all of this also meant, and that was something that I was not able to grasp at the beginning, that we're going to have a lot of dependencies on existing things that we could not change, and we had to adapt to them. Something that we're not used to do in paper, because when in paper I don't like something, what I do is to write an assumption that says, I assume that this thing now can do something else. And then I run the rest of my paper. And in general, that kind of flies because we really prime these kind of ideas that are forward-looking, and we want to think ahead. But now we could not think kind of ahead because this thing needed to be implemented now. The pandemic is here today, not like in 3 years when phones do something else. And the phone, and the fact that we were using existing infrastructure, and let me be very clear that this is not a kind of restriction that I put, and I chose to put an app. This was for us something given. It was like, you're going to build an app. And in one of those first meetings I was there, it was very clear to me that the app was going to be made. I could be involved and try to make it better, or I could not, but there was going to be an app. Governments were decided to do this thing. Now, the moment you do an app means that you're concerned to platform. The platform is the phone. And the phone has a limited amount of sensors and capabilities. And the one that was decided to be used was Bluetooth low energy. That means already that we have a limited payload. There is already a packet that has a bunch of fields, and there is that many fields that you can use. So we could not have a bigger payload. We could not imagine. Then there is also that it is the phone. The phone is in the pocket of the users. The users want to be safe from the pandemic, but you know what the users want as well? They want to call, they want to listen to music, they want to listen to podcasts, they want to play Angry Birds. And the thing that they hate the most in the world is when you eat their battery. So it has to be battery kind of respectful. That means that in order to respect that, you cannot use the CPU so much. You cannot also be sending and receiving so much. That means that we have a limited amount of round trips. That also meant, and in the beginning, I was also so far from understanding this, that Google and Apple had to be involved to make sure that the way in which we use Bluetooth low energy is actually battery and CPU usage respectful for the users. Because the current way in which BLE is used, or before all of this started, if we now wanted to have it happening more and in the background, it would take too much battery. So they actually did a lot of optimizations in this exposure notification to be able to have as many readings as we have today. And honestly, we would love to have more, but this seems to be kind of a barrier in which they cannot go beyond that, because otherwise the battery of the phone could be drained. And already, if you go to the Apple Store and Google Play comments from these apps, battery consumption is one of the biggest complaints that users have. The other thing is that we needed to run in the background, right? Because you want to do this thing like seamlessly while you walk around. You don't want to have your phone open and with the app on the foreground, which also means a lot of security problems, right? Because then you cannot block your phone at any time. And that meant that particularly Apple had to be involved, because Apple at that point was not allowing to use Bluetooth low energy in the background by any application. They had to change their firmware for us to be able to even start to implement this kind of applications. And then there was another one that I also didn't foresee, which is the compatibility between Android and iOS. In the very first prototypes that we had, when still we didn't have Google and Apple involved, and we were just building our own protocol, we discovered that the Bluetooth stacks from iOS and from Android, they were friendly, but they were not the best friends ever. So we would see a lot of packets being lost and a lot of things that were not matching very well, that they actually worked a lot in the back to actually make it happen, making sure that when an Android phone is broadcasting this BLE, an Apple phone will read all of them and the other way around. And all of these things, again, is a big dependency, because once we have on the phone, once we want this thing, for this will meant that we cannot select many cryptographic protocols because they would need too much data. And all of this meant, well, this one that we need to have this kind of broadcast and reading. There's no way we can do round trips. It also has to do with the fact that we also want people that cross each other to be able to hear this type of beacons. but also that we would depend on Google and Apple, because the moment we decide to do something on the realm, they are the kings, right? And this is not something that we typically do. Just for an example, this is the project that we did with the journalist. This is also a very advanced privacy preserving system that is going to be deployed in the next year, but it had nothing to do here. We had very loose time constraints for the design. We could use anything we want. We could create it from scratch. They have 1,000 journalists that need to use. It doesn't need to be real time. Journalists are very patient when they do their investigations. So here we could design new anonymous communication systems. We could design new cryptographic primitives. In the contact tracing app, all that was a luxury. We just had to go for the simplest thing. And that's how we got to the very simple design. And as I said, I'm not a cryptographer. I don't dare to enter in the crypto details here. But this type of protocols have to be discussed to end. But for just the people that don't know how it works, the phone creates a key. From the key derives these ephemeral identifiers that it broadcasts. And the ephemeral identifiers change over time so that they don't become a way of tracking people. Then other phones listen to this. They listen to it. They also record some information about the power, which is kind of a proxy for distance. The more power, closer the person is. When a person is positive, they are allowed by the doctor to, if they want, upload to a server information that allows to derive the numbers that they have emitted. This is the set of keys that your phone has made. And then the rest of the people download these keys, are able to also derive the codes, and then they check if they have seen them on their phones. And then they have them on their phones, then they would do a computation to see if the amount of codes they have and this power signal kind of amounts to being for too long, too close to someone that was positive, and in that case, the person would be notified. And here the key security and privacy decision happened here on what is uploaded. And we propose that what should be uploaded is what the person broadcasts. And this is extremely important for this purpose limitation idea that we had, because these numbers, these beacons that I am emitting, they are not related to my identity. They are actually only related to this random key generated by my phone. They don't have any information about the location. They are pre-scheduled, and they just happen when they happen, independently of where I am and how long I have been there. And they don't have any information about others. It doesn't matter how many people I meet. I will always upload the same number of codes, the ones that I broadcast. And that means that in this server, there is no information available for abuse. This server does not need to be trusted from a privacy perspective. It only needs to be trusted from availability. This server is, in fact, just a communication channel so that we can have people communicating with each other, the positive users with the rest of the population, without actually having a super complicated address and kind of directory scheme, how the phones find each other in a very nice peer-to-peer. In a paper, I could work a lot on this. In reality, we had to go for the thing that was fast and easy and with warranties as this kind of reliability. And we can have this server on a cloud. In the case of Switzerland, this runs in the premises of the Swiss government. It is very robust. It is always there. And a very important thing of the system as well, so as we said before, we were very concerned that we were going to put something out there that could be damaging. So it's very important that this thing also can be removed. And this is something that we, in academia, we don't think very much about. It was going to happen after the system is there, but here it was important. And this design ensures that the system kind of sunsets by design, because there is no information that can flow if the users either delete their app or decide not to upload anything anymore. And because the information in here is actually useless, kind of, it doesn't have any value. The moment that users decide to not participate, the system disappears, even if the governments want to still have it on and they would like to have more data, they would like to have more, it does not matter, the system just dies. And this is the system that actually was taken up and put by Google and Apple on what is called the exposure notification framework. that nowadays is in every phone and is at the basis of every contact tracing app. Not every, but of many contact tracing apps. I mean, the ones that are actually based on this type of privacy preserving principles. As we know, there are many others that are much more invasive, and I'm happy to discuss them in the questions. And this protocol is very simple. And if you have seen the specification, right, this is little more than a couple of hash functions and a key derivation. It could not be simpler. But the system is not simple. The protocol, this crypto that we fought a lot for, is kind of a very small piece in the puzzle. The crypto has to be on an app that lives in an operative system that connects to a health system, but it also has to abide to the rules of epidemiology, right? It needs to actually be epidemiologically meaningful what it does and how it does it. And then it needs to be abiding to the law, of course, and we cared about the societal impact and how people could accept and play kind of what kind of social acceptance would play a role with the app. And this is why the DP3T initiative was not me and my 3 PhD students, but actually was a huge team, very interdisciplinary, in which we had people not only from different, it was interdisciplinary in the security side, like we had people from privacy, from crypto, wallet security, software security, but then also beyond CS, like systems or requirements engineering. And then beyond that, we had people that are epidemiologists, ethicists, law experts, so that we can really kind of make sure that the things that we were producing actually were useful to solve the problem. And I want to talk a little bit about what this integration with the health authority means, right? So far what I said is when someone is positive, they would receive a code from the user, and with this code, they can upload to the key server all of these keys that then other people are going to use to see if they were close to positive people. Now, this little drawing here also meant that we needed to come up with an authentication mechanism. I was like, yeah, sure, it's easy. Like, we also know how to do that. We have done a lot of those. And this is important to ensure that only the true positives, people that have been actually declared positive by a doctor, can upload to avoid false alarms. Remember that one of our core security requirements was no false alarms. And then we started designing these, and at the beginning we were going for a very complicated kind of commitment scheme that would bound the access code to the keys that they had stored on my phone, so that it would be impossible to transfer or steal or do anything, and would be so sure. And then we went to the part of the health of it, and we discovered that, you know, that's not so easy, because it seems that not all health systems are super digitalized, and doctors have way to actually interact with your phone via Wi-Fi or anything, right? No, this is not like that. Actually, most of health systems are not very well digitalized. Many health systems are highly decentralized. In the case of Switzerland, health is cantonal, so regional. So we actually had to go for a very simple system in which have codes. So the doctor generates a code on a central server and then gives this code to the user, and then the user inserts this code on the phone, and then it works. Another very important point here is that the user has to be taken into account, like UX. This needs to be very simple. We need something where also the code cannot be hyper long, because remember that this user that we're asking to upload is the user that just has been told that they are positive of COVID. So they don't really are in the mood actually of entering in very complicated things. You give the code, they upload it, and you say, so thank you very much, because they already did something else instead of just going home and think about what has happened to them and how to deal with it. So, okay, we have solved this problem. We know how to do this. It's maybe not the most cryptographic cool thing. For what is worth, for instance, Belgium, in which where they actually do have a pretty well digitalized health system, they actually have a much cooler authentication mechanism based on commitments. If you're interested in that, Bart Brunel can explain you all about it. Sadly, in Switzerland, we don't have that luxury, so we just have these little codes that are sent to people in a piece of paper or an SMS where you're very, very lucky. So the question now here is, does this matter for privacy, right? We now have our protocol. All of the protocol is great. We have all of this property, but now we have two interactions that kind of are not really taken into account by the cryptographic properties, right? And the thing here is that, as I described the system, the only people that upload keys are the COVID positive people. That means that one of the most sensitive information in the system, who is positive, is actually very visible from a traffic analysis perspective. And already in our white paper, of course, we saw this, right? That's part of one of the things I have done most of my research, traffic analysis. We're very good at these, and we just wrote there, it's okay. You just kind of have to use dummy uploads. And then reality came, and dummy traffic in reality is not so easy. Because in a paper, we know the constraints. We know the constraints because we write them down, right? We have something, and then you say how users behave. You kind of put a model. You say all users are Poissonian, and that's cool. In reality, we have no idea how users behave, let alone how users behave in the new normal, in which we don't know how any of these things happen. We don't know how often people use the phone, how much they use it. We don't know how much time they take between the positive and putting a code. We have no idea of how to model this. And on top of everything, we also now are on the phone. The phone is thing that I have never worked before with, but it has a battery and it has bandwidth, and both of them are not infinite. They are infinite on a paper, and also because on paper, many times we just think about computers plugged in with electricity. In reality, the phone has nothing of that. So we had to design this again with these two things in mind, so we would not upset the users, because if now we consume all of their battery, all of their bandwidth in sending traffic to hide their privacy, we're just gonna uninstall the application. The next thing, and that actually means that indistinguishability, like having complete indistinguishability, is kind of a dream, because the amount of traffic we would need to make it happen would actually break one of these two conditions, and the users would actually not really like the application. So we had to go for something softer. We went for plausible deniability, assuming that real uploads must happen, and also they must happen on time. There's no way you can delay them. Remember that one of our first goals was to have these timely notifications, so we cannot be delaying uploads because we want people to be notified as fast as possible. There is no anonymity possible because, as I said before, we cannot really do these things over Tor or over any other network that we could have nowadays. And then we need to have constant size and times operations, which means that we need to make sure also on the phone and everywhere that it doesn't matter whether we do something real or something false, our programmers had to go around and make all of this constant time. You guys were aware how we do this as a low level. Now we had to do this as a high level. And reality also means that this thing here is a kind of a little bit of a lie. There is only not that step. There is also the step in how this really works is that the physician would go to another server, the server where I said that we generate codes, give me the code, then I put the code. The code goes to the server to make sure that the code is actually a valid code, and then receives a signed token. That is the thing that I can use to go to the key server and tell the key server I'm authorized to do this upload. That also means that all of our dummy traffic that we didn't think in the beginning has also to repeat this dance. Every time we're going to upload something to the server, we need to make sure that the dummy traffic is there. That also means that these constant time operations that we were talking about need to be rippled through the system. This COVID code server needs to have constant time operations regardless of this access code being a good one for real when I'm going to upload something, or this access code being a dummy thing that I just send when I'm asking for a fake authentication authorization code to then go up here with a fake upload token. And this fake upload token also needs to be distinguishable from a normal token as much as this list, all of it, so that when the key server also then decrypts, can distinguish whether it's a fake upload, which means that these keys should not go into the database, or it is, and it goes into the data. And all of these have to consign in timing and volume. Timing is something that we kind of do with programming that's easy. Volume actually also involve a lot of kind of funny tricks, some of them with crypto, that also has to do with the dependencies that we had with respect to Google and Apple, and with respect that some things that they give and how they expect things in formats meant that, again, we didn't have fully freedom at the time of designing the format of these packets here and there, which actually means that we had to make some tricks and to change a little bit our crypto and our packet formats to make sure that this is really as constant as I am saying. And we thought we were done, but we were not, because again, we had a dependency. We had a dependency in Google and Apple that not only made us change some things in the format, but also they made a decision in their first version that for them it was a security feature. And the security feature is that the keys of the phone that had a validity of a day, so they can generate random numbers for a day, they could not be returned by the phone until they expire. So that means that if you get this, diagnosed positive in the middle of the day, to get the key of that day, you need to wait to the next morning. And that put us in a very bad place, because now we had two options. Either we wait until this key is ready. That means that we delay all keys one day, which is undesirable from an epidemiological perspective, because where we want us to be very fast. Or we have a second upload. Having a second upload, so we upload, what we do actually is we upload the keys of all of the days but today. And then the next day, we upload a second key. For this, we have the key server giving us a new token that allows us to upload a new key. Now, this is something that, again, has to be followed by the dummies. And that means that there needs to be a lot of programming and scheduling in the back of the application that becomes more and more complicated, just to make sure that we can deal with the fact that Google and Apple that had one security part in mind, but did not really have the full system, how it all would work. The fact that the uploads have this kind of authorization in mind, they just had not even thought about it. So we had to go behind and redesigning our system and our kind of rest of privacy features every time they could make a decision about how the exposure notification protocol would work. Another kind of more things that also don't appear on papers. Nobody tells you that, you know, on a phone, you don't have granted that your processes will wake up. They probably will, but maybe they do not. And that means that there is actually, it's not in the figure, but we have a third server in Switzerland. It's called the configuration server. And the phone pulls from there a couple of times a day a configuration. This is in case we need to change any kind of thing with respect to the Bluetooth measurements, or we need to change something that needs to be fast. And then our programmers, because they knew this thing that the phone was not waking up every time it should, and they were kind of worried. They said, okay, we're going to do something, which is like every time the user opens the application, we're going to take advantage of that. At that point, the application has access to the CPU for sure to go and download this configuration. But this is something that only happens when the user opens the app. So it would not happen when we would be sending a dummy upload. So when we discovered this, we had to redesign how they find these configuration files and make sure that we minimize the impact of this phone not waking up very often, while at the same time making sure that those downloads from the configuration are independent from the dummy uploads or from the real uploads of users, so that we could still keep our privacy preferences. And finally, just another slap of reality was when normally, and also in my work, kind of, I always plot these servers here on my papers also as a square, and things, you send things there. But it's out that they're not a square, they're in a cloud, and in a cloud there is a lot of stuff, right? If we look at this thing, here we would have the phone, here we have the doctor that accesses this server. The red server is the one that generates the codes. And then they would have a code. The code would be sent to the phone. And then the phone uploads things to the black server. This is where we have the keys stored so that other people can download. But it turns out that in the cloud, there are all of these things at the front. All of these things are the load balancer, and the firewall, and all of them do download information, sort of do store information. They do this for DOS prevention, for other security things that, of course, we need them. We needed to have this information because we cannot afford that our cloud is attacked. But now means that that information, we also need to take it into account when we think about the privacy properties of the system, because the log of these elements that were not thought in our original design, we need to make sure that when we cross them with the logs of how do we generate codes and with the logs of how keys are uploaded, do not actually reveal which uploads were real and which of those were not real, because otherwise we would be losing all of the effects of our dummy traffic. So we spent another day with the developers of this side of the system, designing how to keep the logs and get into a good agreement in which they have coarse enough information so that it is good enough for them to do the management, but it does not interfere with all of the privacy properties that we have. And that a little bit is Swiss COVID and all of the things we did on top of the protocol that Google and Apple took. And I'm very thankful that they did a lot of the part in the phone that we could not do in another way, but they only solved like a very small part of the problem. The system is much bigger. The current status, actually, this is not completely current, is a bit outdated from October. The number of active users is the same nowadays. I think we now have 1.9, but at the end of the day, it's 22-23% of the population. And I'm going to give you the data from October, because after October, we had the second wave. With the second wave, there was a full collapse of the system. And that meant that tests were not working well. And if we don't have tests, it doesn't matter if we have an app or not, because that's kind of the first step of the chain, is that you can identify positive cases. We don't have positive cases, so tests were not fast. And then also the way of giving codes, because cantonal doctors were overwhelmed, it was not working so well. So it's not really kind of a real well of knowing how the system is working, but more kind of how the system works when everything is broken. So in October, we had more than 15,000 users uploading their keys. That's 15% of the positive in Switzerland. It's a bit smaller than the 22% of the population. In previous months, in September, these two numbers were the same, indicating that indeed, probably most of the people that were using the app actually were participating with their keys in the system. But the good news is that we had many surveys in the field. None of this data of this part is actually collected automatically. This is via surveys at testing facilities and after people get positive. And we had at that point 285 positive cases that reported the app as the reason why they were testing. So they said received notification, and this is why I came here. Also the speed. We know that people that are notified via the app are notified half day to 1 day faster than a contact tracer calls them. For the ones that the contact tracers get the phone, we don't have much information about the others because the contact tracer never called them. So in that case, the gain is infinite. And in a cohort in Zurich, during a month in Zurich, where the flow, like tests were very fast and the codes were sent very fast to the users, we had that for every code that was uploaded, so every user that uploaded actually generated 22 info line calls, so calls to the system saying, I have a notification, out of which 5 were put into quarantine. And of the cases that were tested, because mentioning the app as a reason, we have 1 positive per 10 cases, which is more or less the same percentage that we have in manual tracing, indicating that the app, when the cycle works, it actually can be very helpful to alleviate load from the manual contact tracing, find other people, and find the same amount of positives. So in the summary of all of what I have said, we believe this is the first privacy by design product that has been developed at large scale. This is the countries that have countries and states in the United States that have apps based on this protocol. By now, I believe that there are a bunch more states in the US that have not added to the picture. These 6 countries actually use our code base, the code base we developed in Switzerland. So they also include all of these other protections that I have talked about here, dummy traffic and these kind of things. And kind of key lessons for me, well, key lesson for the world is data is not a must. We can do things that have no data and are still very useful. And we should start thinking about how to do that kind of products. Lesson for me is that privacy engineering in an agile service world where kind of things change all the time, you rely on others, you depend on others, things change meaning is exhausting. The amount of times we had to redesign mechanisms in the system to make sure that the Swiss have the privacy that we promised them this has been just exhausting. And integration in the health system is key, and it is very hard because the health system is not really something that is prepared to go in these very advanced technologies. And we have done a lot of work hand in hand with them to make sure that we could set up these servers, that we would have a good integration with the doctors. And it's still one of the weakest points, as far as I'm concerned, in Switzerland and in many others, is how hard it is, that part, to get doctors to take a code and to give it to the user and the user to put it in. Like the parts of the app work well, those parts are much harder. And I believe that a bit of it is because we developed this in a very fast way. And I guess you're cryptographers and you want to know whether is it all solved? Should we do something else? Should we find another topic? I wish we could eliminate the Google Apple dependency. Nobody likes this. I don't know if we can eliminate it as long as we're on the phone. I don't know if the based contact tracing is a possibility. Can we build devices that are cheap enough that we can distribute them to the full population? And what is the type of lightweight crypto that would have to go in these devices to make it work? And can we make them lightweight and also interoperable with phones? Maybe yes, maybe not. If we cannot reduce the dependency, can we reduce trust? Can we verify the randomness of the keys? In the beginning, we were thinking a lot about this, right? Because now the keys are generated by Google. They promised to us they're random. We really don't know, for all that we care, they may not be. Is there any way, now that we are on a platform where we have absolutely no control and maybe no trust of anchor, can we have a proof of this randomness? Can we give them half of randomness that comes from somewhere else to make sure that they cannot cheat? Can we verify the libraries without seeing them? Because seeing them is not being an option, especially with Apple. What can we do? Do you guys have tricks to make this happen so that we can actually know what is going on behind the scene? Can we eliminate beacon authentication related attacks? The fact that these beacons are not authenticated because we didn't have a space on the payload. Can we do something crypto? Is there any crypto that we couldn't think about in 3 months, but maybe in 1 year we can, so that for the next pandemic, we don't have those kind of attacks? And can we do this without Google and Apple's collaboration? Because all of the solutions we have right now actually rely on having round trips and having more data being sent around, which actually means that Google and Apple need to change their scheduling and their battery and how they do management of the Bluetooth stack. Otherwise, all of those are going to end up being a battery drainage. And I have a couple more slides, if you will allow me, about the future, because the pandemic is still here and people are still calling for technologies to rescue us from the pandemic. And I'm all into technology. I'm a professor of computer science, but again, the same thing is with the apps. There was a huge danger of creating a kind of an infrastructure that could act as a surveillance and a source of information that could end up with a lot of control over populations. We have the same thing with the new one. The new one is the idea that now we have restaurants. We discovered that the disease not only can be transmitted very locally. If you're in a non-ventilated place, it can get further. So now we have more of these kind of tracing technologies. And a lot of these tracing technologies require people to check into places, and they create huge databases of both the positive people with names and addresses and everything, and also of the negative people, just in case they are needed someday, with unique identifiers. And they have a registry of every event that happens and participates in the system, and think that there are many events that right now we don't have a register of. And there are very good reasons why we wouldn't want to have them actually not registered and not associated to particular people that organize them. Think about reading groups, for instance, with some political orientation. We have made a proposal for this, in which we give privacy to the users and to the locations. The white paper, you can find it going to this link, where we have a demo app, and then you can get to the white paper. It is not the last protocol version, but still, we would love if you take a look, give comments, and criticize as much as possible, because the only way of making robust system is to have them criticized. And sadly, at this point in time, we don't have the luxury of going through the full peer review process and waiting for a couple of years, because all of these systems are just being promoted at the speed of light. And if we don't have alternatives fast, then we're just going to have a full panoptica. And the final one is the digital immunity passports. This is common. We already have the World Health Organization asking for a group of experts to propose a standard for interoperability of something we don't have yet. And this is extremely dangerous, right? This actually will create the central database. We could permit global tracking of user, because one of the goals is for allowed mobility within countries. It will create a lot of discrimination. Not everybody is going to be able to have a vaccine at the same time. Not everybody is going to be able to pay for a vaccine, maybe for all of their family members. And we're going to have a digital divide of the people that actually have the monies and the capability to have this digital thing that allows them to do traveling or to access services, and let alone the function creep. Once we have a way of knowing who's positive and who's negative, what if now restaurants and gyms and or even universities start to ask people to have one of these, to be able to access all of these things that at least I believe should be available for everyone. Examples of this kind of function creep we have in India with the Aadhaar identity card, that started to be kind of something very nice to give people that were at a disadvantage some advantages, and ended up being this kind of identification now needed for everything, and creating all of these databases and power. And my kind of problem here is that I don't know how to create this in a way that is not abusable. But you guys know a lot of crypto, and this is not about privacy. This is about how can we limit the purpose of something that only has as an output 1 bit, whether I am vaccinated or not. Can we create something that allows us to say, if I create this system, it can only be used for one thing, and the one and only, or not? And with this, I'll be happy to take questions.
So thank you very much. That was a brilliant talk. I really enjoyed that, especially the various kind of things that you don't necessarily read in your papers about all the kind of constraints that you have that are normally not considered among sort of crypto people, but that are very real. There is a question in the chat, which I'd like to simply relay. And the question is as follows. Can you elaborate how exactly are the random codes generated, and how are the keys protected?
So the keys are protected by the power of Google and Apple. It's a purely software and architectural protection. How the keys are created, I really, so you just fit these keys, the big key into, if I remember correctly, into an AES function, and then you just introduce numbers, and you just take what comes out as your random identifier of the moment.
Okay.
But this is true that the only protection that we have is that Google and Apple have decided that their API is like that, and there is no other way that we have. And I'd love to hear cryptographic hardware options to make this not dependent on their promise, that this is going to be here forever, because I can tell you how much I believe promises from Google and Apple.
Okay, I'd like to encourage people, if they want to ask you questions, to do so in the next few minutes. We have got a few more minutes left. I have some questions. I think some other people here are also waiting to ask. So if you don't mind, I will have a go. So one of the things I'm curious about is because you've got this kind of heterogeneous network that represents the health authority, and then you've got this one server that kind of dishes out numbers and so on. Who's actually running that? How does that work?
So different countries have different ways of doing this, which makes this problem even kind of funnier. I mean, we not only have, we have consulted with the government in Switzerland, but we have also consulted many others that also have the same kind of problems at the end. How can they build the dummy traffic? But they have different ways of generating these codes and different places where this thing is run. In the case of Switzerland, both of these servers are run by the government IT, because Switzerland has a cloud of the government. Not everybody has a cloud of the government.
Yeah.
Other countries have this on Amazon Web Services, both the one that generates codes and the ones that not. And as I said, they have different type of authentication. If I remember correctly, Estonia actually, which is also highly digitalized, their authentication is actually linked to their digital health system. So they log into their health system and then they get the authentication from there. So there are many different things. And the kind of a bit of the sad part, and this also a big realization for me, is that some countries did not have the capability to run this on their own, and then ended up actually running this on public clouds, which I didn't put on my slides, dependency on Amazon, but we could.
Yeah, okay, that makes sense, thanks. So, I mean, you had a number of constraints: device-related, system-related, user-related. Suppose you could change one or two of these constraints, so you had a magic wand that would have made your life considerably easier, or the solution nicer. Which ones?
I think that the battery constraints, I mean, the battery and the CPU, right, are the kind of the one that would have given us more freedom to design both at the Bluetooth layer. So to have, as I was saying before, like more beacons. Like one of the proposals we had was to have beacons that instead of having one number would use secret sharing. So you would divide your ID in various beacons, and then you needed to listen to some of them to increase privacy. That was a no-go. Like there is no way that they can transmit. So actually, to me, battery and more control on when and how do apps have CPU on a mobile phone, that those two things could have made our life nicer.
Okay, cool, thank you. I don't want to be the only one asking. I know some people are hovering here, so please chip in.
I did have many questions, but I think Carmela answered them, before I could ask them. So just one other question, one of the things you didn't answer. I was wondering, there are alternate approaches, right? Do you want to comment on other kind of approaches, and if they are, what do you think of? So instead of, I mean,
can
as
you
a
give
very,
me example?
I don't know if they are used in practice, but somewhat more centralized maybe, but some of them, I could imagine instead of using Bluetooth contact, you just upload some sort of your coordinates and then you check for matches.
So the location-based one, I mean, besides being extremely invasive, for what I have learned from epidemiologists, are not even very reliable. GPS signal, especially indoors, don't really have a precision that would allow you to say these 2 meters, right? And I'm very surprised, because when it comes with the Bluetooth, everybody flips about how imprecise is Bluetooth and the number of false positives we're going to have because there are walls and I don't know what, and everything is going to be horrible. But then if you tell them we're going to use GPS, which is much more imprecise, and you have much less good fine-grained information about who's close to whom, then they seem kind of happy. But to me, those, I mean, they really, I don't see how they can have any gain. They do have one gain, which is that you can go back in history, and when somebody's positive, try to do this other thing, what I was saying, this presence tracing. Where have you been? And do I have to tell a full restaurant to quarantine their employees and their clients and things like that? The location would give you that. But from a contact tracing perspective, I don't really think that.
So in your crowd notifier, the kind of detecting hotspots, would that kind of approach would be useful?
So how we, yeah, that's the thing that you could try to substitute with location, right? Because that is precise enough to know if you're in a restaurant or not who you are close to. But then again, like the kind of systems we propose, like they will collect a quarter of the data. You don't need to give any other information. And I just think that this is what I was saying in the beginning, right? What is the potential of misuse of this information?
Sure.
Because we also have to think about that the systems may fail. And in fact, these apps so far, they have not had adoption. They do help in cases, and of course, every life counts. But what happens when the systems fail, or what happens when we need to destroy the system? Any database we create is a risk.
Sure. No, I was not suggesting that, even in these alternate systems, there should be, it shouldn't be just a naive, everybody just uploads their location. It should be under some cryptographic layer. I don't know if anything like that has been done, or.
I think there are a bunch of proposals, right? That, for instance, you try to do privacy intersection between two traces, but then you have a lot of problems with how noisy GPS traces are. And in order to make the less traces, you need to reduce the precision, and then you completely miss this idea of are you close or not, I think. So I think that when we really think about the practicalities, there are a lot of, I think this is problems people should really work on and try to find it out, but then go deeper beyond the cryptography about what are the constraints in reality now when I really have GPS traces, and GPS have like a 15 decimal, when you download them, which is the good one? Can we make sure that when I do the matching, or can we do PSI with fuzzy matching? That would be cool. Not only for this, I can come up with a bunch of other scenarios where this would be useful. But it's not only about what is the conceptual cryptographic, but does that actually work in practice? If I may add something else that I didn't put in this talk, but another constraint mainly that happens when you deploy privacy enhancing technologies into systems is that you lose a lot of information for monitoring on how the system works. In this case, I said in my slide the number of active users we have. Those means users that actually have the app installed. Those are not downloads. Because the number that we really want to know is how many people are using it, right? You can download and then delete or not be using it. And we also, what we do to do that is we use the dummy uploads as a proxy to compute how many people have this app in kind of a privacy preserving way, because we don't really need to know who they are. We can just do counts based on these dummy uploads that mean nothing for all that we know. But how to think about other parts of the system, how to monitor them in a privacy preserving way, how to do all of these counts, those are also things that are extremely valuable, not only for this system, but in general, because under deployment, you need to learn these things. Otherwise, you cannot really manage the system or help users when they have problems.
So maybe on a related note, with 20% of the population using it, do you think it was effective, or should it have been, was it worth all the trouble at this point? I'm sure in the future, it's probably a very useful thing.
I think there are two angles to this question, is how useful it was for the pandemic. I think that in that sense, well, the effort was useful because anything we do to try to help here, every effort is little. As I said, if we can save some lives and eventually convince people that it's actually something that would do more, that is. But I think there is a second angle here that is very important, and I'm talking about our effort, which is on making sure that now that the system didn't work, and for the reasons that it doesn't work, no app would have worked. Like if people do not install it, if doctors cannot get codes to the people. It doesn't matter if it's centralized, decentralized, has GPS, or every of the information of Facebook on it, right? The things that failed were other. But now we have a system that when it fails, there's no damage. And this is, again, something very important for the design of systems, right? How we think about what happens after the system is there, and what are the consequences that we have introduced a technology in the world. And on the sense that I think that the effort is absolutely amazing, right? That at the end of the day, we have gotten something that is not going to be there creating damage at the end of the pandemic, whether it helped the pandemic or not.
Okay. I think, I mean, we are just beyond 4 o'clock. Srinivas, do you?
I think we can. There's actually one question in the chat.
Yeah,
want
we
to
can
take it
keep
up?
going for a little longer. That'll be fine if Carmela is available.
Yeah, so the question is if I have any thoughts on creating a generic mechanism for centralized and decentralized systems to interoperate. We actually do have a document on that. We do not believe that you can do that. You just get the best of the worst of both worlds, because these systems kind of rely in completely different information. And when you make them interoperate, you just make both of them get the information they didn't have. So we don't really see a way of doing this that doesn't lose the privacy of one or both ends. So again, I'm happy to be proven wrong. But in all of that, we thought, and believe me, we thought a lot about it, because Intersata, we live in Switzerland, and one of our borders is France, where we have around 100,000 people that cross the border every day for working in Switzerland, and we would love to be interoperable. But we cannot do this at the risk of the privacy of our users.
Okay. I don't see any other questions in the chat. I could, ask loads more questions if I, but I realize we are past 4 o'clock. So Srinivas, you need to tell me, or need to tell us how this is, how long we can have.
So we have been flexible in the previous talk. So if you have some, questions in your head, you could go ahead and ask.
I ask a final one, and I don't expect a completely exhaustive answer, but so I teach crypto engineering to my students, and we do kind of touch on consequences of what you develop, and not just how well you develop something. So if you, I don't know, had 3 or 5 points that every student should know who's developing something crypto related, that might, how can they assess whether or not what they are doing has an impact on the privacy of users or of people who deploy a system? What would be the best questions you can think of that I should pass on to my students they should ask themselves?
So when thinking about this privacy engineering, on one of the first papers we wrote about how this is, this is about data minimization. It's something that crypto does very well. And then we discovered that data minimization didn't really make the job, because the data is still in the system, right? So saying that if we're going to use a lot of crypto, maybe we're not doing that. So we say it was risk minimization, like we minimize the risk of the data going to a party we do not trust. Mm-hmm. But after this year and building all of this, I'm realizing that what we truly do is purpose limitation. We create systems that can be only used for one purpose. And this is what I was trying to say, that privacy, we concentrate a lot on privacy. I mean, I have made a full career out of that. It is great, but at the end of the day, I'm realizing more and more that it's just a means, and that when we think about what systems to build, and when I think it out with, we actually think what can happen beyond that, how the data can be used. And you can have a fully privacy preserving, like with these digital immunity certificates. I'm sure we can build it in a privacy preserving way, right? We combine a couple of multiple trees with the zero knowledge proof and some anonymous credential, and we're done. That still does not mean that we have really solved the core problem of it, which is how is it going to be used. Mm-hmm. So thinking out of the box about what else can be done with the data that you're putting there, and trying to separate this, the privacy of the users from the consequences that the system can have to the users. And then the other one is not only always think about the user, think about collectives. Mm-hmm. And what's the impact for the collective. because we have a lot of these nowadays of a lot of privacy technologies for data mining, which sure, they're great. We don't know anything about individual. It still put all of the power on the big techs of the world to profile full populations and make a lot of decisions based on that. And we should think about what that means. I don't know if I have increased your list or not.
I typed things up, so yeah. No, that's perfect. Thank you. So I will pass these things on, and I'll also have to think about this myself. That's very, very useful. Thank you. That's me done. I pass back to Srinivas, who's the boss.
Very nice talk. So this brings to end the entire conference. So I have a small ritual to perform. Can I take a minute or two, Manoj? If it's fine.
Oh, good. Yeah.
Oh yeah, sure. So I would like to, glad that every session went very smoothly. So I should thank all the session chairs and the speakers. And then I should thank Elizabeth, Manoj and Karthik for putting up a fantastic program. So this is the largest IndoCrypt in terms of number of accepted papers. And it was also very nice to see the formal methods community also participating in the event. And I hope it's going to be a trendsetter for future editions of IndoCrypt. Okay, and one last thing on behalf of organizers, I would like to thank the team of volunteers, so mainly comprising of students who did a fantastic job. So let me take the liberty of quickly reading out their names. Anju, Janvi, Hemant, Aditya, Deepak, Shyam, Girisha, Santosh, Annapurna, and Vivek Yadav. So they did, they worked really hard, and so many of them are undergrads, and their examination schedule actually coincided with the conference, yet they really put in their efforts, and thanks a lot to you people. So team, maybe you can just unmute and show your video and say a quick hello to all of us, if it's convenient, of course.
Hello everyone, I'm Shyam. Hi.
Yeah, I'm Annapurna. Janvi.
Yeah. Hi everyone, I'm Hemant. And
Yeah, I'm Aditya.
So they are all over the country. So because the instruction has not, the physical instruction has not begun yet. Okay. So anyway,
on behalf of the PC chairs, I'd like to, and the PC, I'd like to really thank them. Made sure everything was very smooth. Yeah. So great job, guys.
Thanks a lot. Our pleasure. So, and I think anything else to add? So I'm done. So Manoj, anything for you to add?
No, it was a great experience for hopefully everyone, and certainly for the PC. It was all smooth and nicely done. So yeah, thanks to the organizers, thanks to the authors, thanks to the invited speakers, for making it happen. And yeah, in the we also would like to thank CRSI for letting us be the PC chairs and so forth. So yeah, so we don't have a social event, unfortunately, but pandemic as it is, but hopefully next year we'll have a physical conference.
Yeah, that's our hope too. Okay, so thanks guys. So then, okay, so I'll close the webinar then.
Okay, thank you.
Yep.
Thanks,
See you all
everybody.
next time.
See you all next time.
Oh, yeah,
Thanks, Karthik. Thanks.
thanks everyone.